Mr. Tarrou. In this video, we're going to be taking a look at a few examples of indefinite integrals that involve, that have integrands that involve fractions. Now, we have four rules that we have that already have integrands involving fractions. We have the indefinite integral of u prime over u is equal to the natural log of u plus c. We have the indefinite integral of du over the square root of a squared minus u squared is equal to arc sine of u over a plus c. We have the indefinite integral of du over a squared plus u squared is equal to 1 over a arctangent of u over a plus c. And we have the indefinite integral of du over u times the square root of u squared minus a squared is equal to 1 over a arcsecant of the absolute value of u over a plus c. This video is going to involve integration by partial fractions and integration involving trigonometric substitution. Now, I already have videos on partial fractions that go way beyond the complexity that we need to worry about in AP calculus. So when you teach AP Calc AB and AP BC, Calc AB BC, they're nearly complete university courses, but there are some minor differences. And in terms of integration involving partial fractions, the only problem you need to worry about is when you have an integrand that has a constant over a factorable denominator that gives you two unique linear factors. And that's what we're going to focus on for this first example. If you need to see partial fractions that are a lot more complex, I'll put video links in the description below. So when you go to take an integral, you should always think about that 17 or 18 standard integration rules that we have and try and choose the simplest one and then build your way up into complexity. So when you see that we have a denominator that is a polynomial with a degree of 2, the first thing you should think of, or actually anytime you have a fraction in your integrand, is just do you fit that u prime over u pattern? Well, if the denominator is our u, which is a second degree polynomial, we need a first degree polynomial in the numerator, and indeed we do not. We just have a constant, so the degree of our numerator is 0. So this is not going to integrate and give us an answer involving natural log. So you then should be thinking, well, what's the next integration rule would you have, like the next step up in complexity? What integration rule may we be going towards? It looks like we could do some completing of the square like we talked about in the previous section, where we complete the square and get our denominator to be a sum of squares, thus giving us an answer involving inverse tangent. So let's give that a shot. We're going to have the indefinite integral of 4 over x squared minus 2x, leave some room for completing the square, minus 8 dx. Now, when we complete the square, of course, we're going to take half of b, so half of negative 2. We're going to square that and get an answer of 1. So we're going to both add 1 and subtract 1 in our denominator. When we do that, of course, completing the square creates a perfect square trinomial, and factoring that, we get the indefinite integral of 4 over x minus 1 squared, and then of course negative 8 minus 1 is negative 9 dx. I'm looking at this problem realizing the integral of u prime over u is not the rule that we're going to follow. Move into the next step of complexity, which is where we create a sum of squares in the denominator, and indeed we do not have a sum of squares. We have a difference of squares. So this is a problem that we are going to need to tackle with either partial fractions or a trigonometric substitution. Now, as I say trigonometric substitution, and you think about drawing an angle in standard position, having that reference triangle and talking about a squared plus b squared is equal to c squared, you can have some individual legs of values, and then the hypotenuse is going to be the square root of the sum of those two sides squared. not have a situation where we have a difference of squares. And indeed, that's why, partially why, that's a big reason why we have this a squared plus u squared in the denominator, yielding us an arctangent with our second rule or third rule there. So I'm feeling like, because of my understanding of Pythagorean theorem and seeing that difference of squares in the denominator, this is not going to be a question that is solved using trigonometric substitution. Well, we might be in trouble unless the denominator can be factored. And indeed, this one can be. We have the indefinite integral, and I'm going to go ahead and move this constant coefficient of 4 out front. And we have 4 times the indefinite integral of x minus 4 times x plus 2 dx. So if we can use partial fractions to pull this integrand apart and create two simpler integrands, we're going to be on our way of integrating. So we have 1 over x minus 4 times x plus 2. Now we want to create that. Now we have a constant in the numerator, and we have two unique linear factors for our original quadratic in the denominator. Again, this is the simplest setting for partial fractions, and for AP calculus, it's the only type of partial fractions you need to worry about. You can have partial fractions that develop or where you have to go through a whole system of equations, possibly 3 equations and 3 unknowns, and do some really complex work to pull apart the addition here. But that's beyond the scope of AP calculus. We have 1 over x minus 4 times x plus 2. Now that is going to be equal to, we're going to find some kind of constant a over x minus 4 and add that with some kind of numerator, some unknown numerator. In this case, because it's the simplest setting, it'll be a constant of b over x plus 2. And we need to find out what two fractions add to this and will give us this answer of 1 over x minus 4 times x plus 2. To do that, we're going to multiply both sides of this equation by x minus 4 times x plus 2, and that will give us 1 is equal to, as we distribute to our first term on the right-hand side, the x minus 4 will cancel, and we'll have a times x plus 2. As we do the distribution through the second term on the right-hand side, we'll have the x plus 2 cancel out this time and have b times x minus 4. Now, this line needs to be an identity that's true regardless of what value of x is used. And again, not to emphasize it repetitively, but this is the simplest type of partial fractions you can deal with. Constant in the numerator, unique linear factors in the denominator. So we can kind of shortcut this process, and since this is an identity that's supposed to work for all values of x, I'm going to choose a very easy value of x and say let x equal -2 and plug it into this identity. That's going to give me 1 is equal to, now -2 plus 2 is equal to 0, and that's why I chose this value. The variable of a cancels out, and we have b times -2 minus 4, which means we have 1 is equal to b times -6, or in other words, b is going to be -1/6 when x is -2. Now we're going to choose another variable of x that's going to let the variable of b go away, and that's going to be the value of 4. Let x equal 4, and that will give us 1 is equal to a. 4 plus 2 is 6. 4 minus 4 is 0. And of course, we then just, the b cancels away, and we have 1 is equal to 6a, thus giving us that a is equal to 1/6. So what I'm going to do now, and for running a little bit out of room in this board, so I'm going to move the a out front and have a times 1 over x minus 4, move the b out in front of the second term and have b times 1 over x plus 2, and we then can use that information to say our third line of work is we have 4 times the indefinite integral of a, which is 1/6, times 1 over x minus 4. B is our numerator of our second term, I wrote that as b over x plus 2, so we have b is negative 1/6, or minus 1/6 times 1 over x plus 2 dx. Both of these terms have a common factor of 1/6, so I'm going to go ahead and bring that out and reduce it with the 4 and get 2/3 times the indefinite integral of 1 over x minus 4 minus 1 over x plus 2 dx. And we've had a lot of integration that involves giving natural log of the natural log of the absolute value of u as an answer. So if u is x minus 4, then du is going to be 1. If u is x plus 2 for our second term, then still that u prime is going to be also 1, leading us to 2/3 times the natural log of the absolute value of x minus 4 minus the natural log of the absolute value of x plus 2 plus c. And if this is a multiple choice type answer and question, and it probably will, you would more than likely see a solution that is simplified as 1 natural log instead of 2. So natural logs yield exponents, right? And when do you subtract exponents? When you divide with like bases. The common base of that inverse math operation of exponential functions would be base e, of course, because this is log base e, natural log. Our final answer is 2/3 times the natural log of the absolute value of x minus 4 divided by x plus 2 plus c. Bam! That's the end of our first example. That is an example of integration of a integrand that has a fraction in it, not following our integration involving natural log or one of the inverse trig functions. We got to work around that. In this case, it came out quite nicely with integration by partial fractions. For our next example, we have the indefinite integral of 4 over x squared times the square root of 16 minus x squared. You always want to look for, again, that simplest process. If you, this is a very complex looking integrand, so your first attempt should be to just do a u substitution and find a u inside a composition. Well, inside of our square root, we have a 16 minus x squared. So maybe this would be a good potential u substitution. If we let u be 16 minus x squared, well then du is going to be negative 2x. And outside that composition, we do not have a function of some kind of linear function. We don't need to worry about the negative 2 coefficient, but we don't have a function of just, x outside the composition of the square root. We have an x squared in the denominator, but indeed, if we were to bring that x squared up into the numerator, it would be 4 times x to the negative 2, not x to the first, as we would get by taking the derivative of 16 minus x squared yielding negative 2x. So a composition where u is inside the radical is not going to work. We certainly do not have an entire denominator, which is u, because our numerator is just a constant. So that's integral of u prime over u is not going to work. We do, however, have this integration rule that says the integral of du over u times the square root of u squared minus a squared. Well, this kind of fits that pattern. There's a radical, there's a difference of squares and something out front. There's a radical, a difference of squares inside and something out front. We have inside the power of 2, inside this radical, we have an x, and outside it is x squared. Inside this power of 2, we have a u, and outside the radical, we have the u to the same power, not u to a higher power, or not the x to the first squared, and then outside x is squared. So we're really not quite matching that. And inside the radical, it is a function squared minus a constant. And inside our radical, we have a constant squared minus a function squared. So the order of that subtraction is not the same. Trigonometric substitution. For integrals involving the square root of a constant squared minus a function squared, let u equal a times the sine of theta, then the square root of a squared minus u squared will be equal to a times the cosine of theta, where theta is between negative pi over 2 and positive pi over 2. This restriction on theta is coming from the restrictions of inverse sine. You won't need to worry necessarily about this then statement. Then let the square root of a squared minus u squared is equal to a times the cosine of theta. If you draw a picture of a angle in standard position, go ahead and for convenience put it in quadrant 1 and set up the sine function. You're going to automatically know what cosine is, and it will involve that square root of a squared minus u squared. If for integrals involving the square root of the sum of squares, the square root of a squared plus u squared, let u equal the tangent of u equal a times the tangent of theta, then the square root of a squared plus u squared is going to equal a times the secant theta, where theta is between negative and positive pi over 2 again. There's no equal signs on this condition because inverse tangent is undefined at positive and negative pi over 2. Again, how you get rid of the square root, though, is going to come out naturally as you set up your angle and reference triangle in quadrant 1. For integrals involving the square root of u squared minus a squared, which is not what I have up there, we have let u equal a times the secant of theta. Then we have a substitution to get rid of the square root of u squared minus a squared. It'll be a times tangent of theta if u is greater than a and theta is in quadrant 1, and negative a tangent of theta if u is less than negative a, where theta is in quadrant 2. Now, I did all the homework in Calc AB from the book that I'm teaching from, and I never had to worry about this second condition line here with those type of problems. So in that second restriction where we have negative a tangent of theta, that's probably going to just come up later on in your calculus studies, maybe in Calc 3 or something like that, or maybe some other books offer some more advanced problems. But we're going to just look at some of these simpler ideas, simpler examples of trigonometric substitution here. I got, again, more in-depth videos. I'll put links in the description below. But don't worry too much about this, probably in your homework if you're just seeing this for the first time in your calculus class. One thing to note with these statements that are, you should see in your calculus book, we're going to let u equal some kind of sine function, u equal some kind of tangent function, u equal some kind of secant function. There's sine and then there's cosine. There's secant and there's cosecant. There's tangent and there's cotangent. Notice the suggestions for doing trigonometric substitutions do not have you setting u up to be a cofunction, but a primary function. I feel like that's probably because the derivative of cofunctions are negative, and that opens the door for a little bit of extra complexity that maybe we don't necessarily have to deal with. When you realize you have to do a trig substitution, this is kind of like a sort of a streamlined version of what you have here that's kind of like a textbook set of directions for trig substitutions. You're going to set up a reference triangle using the sine of theta is u over a, tangent of theta is u over a, or secant of theta is u over a. Notice these are all the same ratios of u over a, and for convenience sake, we want to keep our constant in the denominator of one of these primary functions. That idea of keeping the constant in the denominator is going to help you understand where to place the variables of u and a around your reference triangle, and then Pythagorean theorem will set up that square root of either sum or differences of squares. Once you solve these for u, find du, and then find a trig substitution to eliminate the square root. And actually what you're going to be doing is you're going to have an integrand that has references of x and algebra. And you want to remove all those references basically of the variable of x in algebra and replace them with trigonometry. That's why it's called trig substitutions. Go ahead and integrate and then substitute back into the terms of your original variable. So what do we have here? We have the indefinite integral of 4 over x squared times the square root of 16 minus x squared. Already understanding that it doesn't fit any of our standard rules, this difference of squares is going to have to come from parts of a right triangle, a reference triangle. So we're going to draw that reference triangle in quadrant 1, set up the reference triangle, and remember that it's what? A squared plus b squared is equal to c squared. The hypotenuse is the longest side. So that's a 16 minus something. The difference of these squares has to be positive, which means 16 squared has to be larger than x squared, indicating that the hypotenuse has to be 4, for this problem. So a is going to be equal to 4, and then we have this other side of x. Now, the x can go here in the opposite leg, or it can go here in the adjacent leg. We want to set up a sine, tangent, or secant of theta so that the denominator is that constant. And I do not want to use a cofunction. So if I put the u here, it will be cosine of theta is u over a. And so therefore, I'm going to put the x here so that we have the sine of x, theta is x over 4. Which means that x is equal to the 4 sine of theta, and then dx, the derivative of sine is cosine, so we have 4 cosine of theta d theta, right in the d theta for the purpose of, we're kind of doing a u substitution, but this time it's a trigonometric substitution. So we have 4, we have x, we have a here, a squared plus b squared is equal to c squared. Pythagorean theorem will tell you that this adjacent leg to theta is going to be 16 minus x squared. So the cosine of theta is going to be the square root of 16 minus x squared over 4, or 4 cosine of theta is equal to the square root of 16 minus x squared. So we now have enough information relating our algebra to trigonometry to remove all the references of x and substitute it with some trigonometry. So we have 4 times the indefinite integral, and maybe I'll need to bring that in later, and let's see. dx is 4 cosine theta d theta, so the x is coming out and being replaced with 4 cosine of theta d theta. Now in the denominator, we have a factor of x squared. Well, here I have x is equal to 4 sine theta. Well, then x squared is going to be 4 squared, which is 16, times sine of theta squared. Now the square root of 16 minus x squared is going to be 4 times the cosine of theta. So let's clean this up, and what do we have? The cosines are going to cancel out. The 4s are going to cancel out. And bringing the 16 out front, we have 4 divided by 16 is 1/4 times the indefinite integral of 1 over sine squared theta d theta. Now, 1 over sine of theta squared, 1 over sine theta, this looks like it might be kind of difficult, but let's not forget our reciprocal functions. This is going to be equal to 1/4 times the indefinite integral of cosecant of theta squared d theta. And now all of a sudden we have an integrand in terms of algebra that we cannot integrate, but now we do know that the integral of cosecant of theta squared is what? Negative, so negative 1/4 cotangent of theta plus c. So our integration is done. We still have a little bit of a problem though, because this integrand, or this antiderivative, excuse me, is in terms of trig and theta. Our original problem was algebraic and in terms of x. So we need to go back to our picture and go, okay, well, what is cotangent of theta? The cotangent of theta is adjacent over opposite. So we have negative 1/4 times the adjacent leg to theta, the square root of 16 minus x squared over the opposite side of x plus c. Let me double check. Hey, I love this stuff. Okay, perfect. Now let's take a look at another problem. For our third and last example of this video, we have the indefinite integral of 1 over the square root of x squared minus 25 dx. So again, you should always think about doing the simplest, using the simplest rules first. If u is x squared minus 25, then du is 2x, meaning we need a linear function outside of this composition. We have a constant outside the composition. If we let the entire denominator something to the 1/2 power, we'll create a function to the negative 1/2 power, which means outside the composition of division, we would need another radical, and we do not. And we have the indefinite integral of du over the square root of a squared minus u squared. We have a difference of squares. Our u here would be x and du would be 1. So we might be setting up to give an answer involving arc sine, but this difference of squares has the constant first. This difference of squares has the function first. So none of our standard integration rules work. So here comes trig. We've got an angle in quadrant 1 for convenience. We'll call it theta. We'll set up our reference triangle. The difference here between, again, the a squared plus b squared is equal to c squared. We need this difference of squares to be positive. That means that the first term has to be bigger. The biggest side of a right triangle is the hypotenuse. So x is going to have to be the hypotenuse. Now, the other side needs to be 5. Now, where do you put the other side? If you put the 5 here, remember, we need to set up a primary function, a tangent. Well, tangent involves the two legs, and we have a function of the hypotenuse, so it's not going to be that. Secant or sine. If we do the sine of theta, it's going to be opposite over the hypotenuse, but the process we're trying to follow, we want the constant in the denominator. So it will not be sine of theta is 5 over x, and it won't be cosecant. We won't say cosecant of theta is r or hypotenuse over the opposite side, because cosecant is a what? It's a cofunction. So we're going to put the 5 on the adjacent leg so that we have the secant of theta is the hypotenuse, x, over the adjacent leg, which is 5, and then x is going to be equal to 5 secant of theta, and dx is going to be 5 times the secant of theta tangent of theta d theta. So if we have an adjacent leg of 5, a hypotenuse of x, then our opposite leg needs to be this square root of x squared minus 25. And we want to create a trig substitution for the square root of x squared minus 25 that's as simple as possible. So why involve another variable of x when we can involve a constant? And we have the tangent of theta is equal to the square root of x squared minus 25 over 5, or 5 times the tangent of theta is equal to the square root of x squared minus 25. Now let's see what we can do from here. We have the indefinite integral. Dx is going to be 5 times the secant of theta, tangent of theta, d theta, over the square root of x squared minus 25 is 5 tangent of theta. We've removed all the references of x in algebra, and we're in the full world of trig. Tangent theta divided by tangent theta is 1. 5 divided by 5 is 1. And we have the integral of the secant of theta d theta. And the derivative of secant, in case you need this for memory, the derivative of secant of theta is secant theta tangent theta. The integral of secant it really is quite a different function, but there's a lot of similarities. There's natural log, and then there's the absolute value of secant theta plus tangent theta plus c. So this integral is done, a very quick process with the trigonometric substitution and relying on remembering what trig is. What is trig a study of? Angles and reference triangles, or parts of a right triangle, which is parts of that reference triangle. This integrand, though, is in terms of trig and theta, not in terms of algebra and x, so we need to do a little bit of substitution. We have the natural log of the absolute value of the secant of theta. Well, again, secant is hypotenuse over adjacent, so we have the natural log of x over 5, plus the tangent of theta is opposite over adjacent, so we have what? We've got the square root of x squared minus 25 over 5, the absolute value of that plus c. So we have the natural log of the absolute value of x plus the square root of x squared minus 25 over 5 plus c. Let me double check. And that is good to go. I'm Mr. True. Don't forget, if you need to do some more complex work involving integration by trigonometric substitution that involves long division, integration by parts, power reducing formulas, I got video links. I have links to videos in the description below. Feel free to check those out if you need that. I'm Mr. True. Bang! Go do your homework.